Hi, I'm Megan Kinard, Director of Communications for the Cornwall Alliance for the Stewardship of Creation.
And I'm Cal Beisner, the founder and national spokesman of the Cornwall Alliance. Thanks for joining us.
Welcome, everyone. We have a real treat for you today. Jim Steele, a biologist who for 25 years was a researcher and director of San Francisco State University's Sierra Nevada Ecological Field Campus, will join us to discuss his new publication, Ocean Health, Is There an Acidification Problem?
I've been looking forward to interviewing Dr. Steele, Mr. Steele, he tells me, for a long time, ever since I enjoyed his wonderful book, Landscapes and Cycles, An Environmentalist's Journey to Climate Skepticism.
Yes, it's actually one of my favorite books on environmental issues that I've read. And a few months ago, we used it as a thank you gift to donors to the Cornwall Alliance. Donors told us how much they enjoyed reading it too.
Right, Megan, and now we're using Jim's new book, Ocean Health, the same way. How can our listeners ask for that?
All they need to do is make a donation of literally any size, regardless how large or small, and ask for Ocean Health, mentioning promo code 20-07. I'll put the donation link in the comments for those interested.
And we'll go over that information again later. Right now, though, before we bring Jim Steele in with us, I just want to mention our producer lives in South Carolina, in Greenville, South Carolina, and there are major thunderstorms going on there right now. So he has warned us that he could go without power at any moment and lose his internet connection. So if that happens, please don't give up on us. We should be back up within minutes or even seconds. But meanwhile, you might want to pray that that does not happen. So now we'd like to bring Jim Steele into the program. Jim, welcome.
Hi, everybody. Very grateful to be here.
Thank you.
We're glad to have you. Would you first give us some background about yourself, your education, your career as a professor, the things that most fascinate and motivate you, and maybe how in particular you came to write your earlier book, Landscapes and Cycles, An Environmentalist Journey to Climate Skepticism?
How many hours do I get to tell you that? And I'll try to keep it short, but
as long as you want.
I got a master's degree in biology from San Francisco State, more as an ecologist. And San Francisco State University had a field station called the Sierra Nevada Field Campus, and the dean of science needed someone to make it run and develop an environmental studies program that supports stewardship of the environment. And so I had worked up there as a grad student, and he thought I was the best person, even though I hadn't had a PhD yet. But people call me doctor, but technically that's not true. But while I was there for 25 years, I did research on how regional climate was affecting wildlife. And from that, we restored a whole watershed, we improved the wildlife. And oddly, through that, I became a big student of oceans. And the reason for that is when we have an El Nino, we get lots of snow. And that would cause wildlife to move up and down in elevations. And during La Ninas, we get hardly any snow or we get a drought. And that would cause wildlife to move down in elevations or places to dry up. So that was one thing that pushed me to study more oceanography and what's going on. And I live right near the ocean, so I see the whales go by. I see the way the seabirds react. So that furthered my interest in why I've been writing right now about a lot of more marine life than I have been mixed in with terrestrial life. When I was doing my restoration work, we studied 5 different meadows of how birds were reacting to different changes. And one of the meadows just dried up. And everybody said, oh my God, that's just what global warming is supposed to do. It dries it up and kills all the animals. Well, if I looked into the historical records, and the maximum temperature in this area had not exceeded what it was in the 1930s. So it was clear to me that it was not temperature that was driving, it was other factors. And being trained as an ecologist, you realize there's many, many different factors you have to look at. And so, that's whenever I see an issue, I have to look at what are the natural causes, what are changes in local climate, what's changes in the way we've affected the way the streams flow, cut down vegetation, uh, et cetera, et cetera. And that led me to kind of realize that, a lot of times people were blaming climate change for changes that happen for other reasons, sometimes caused by people's effect on landscape, sometimes just because uh, the climate cycles in like 30-year cycles. And in California, I was working in the Sierra Nevada. Uh, there's the Pacific Decadal Oscillation, which oscillates between 20 and 30 years, where you get more El Ninos when it's positive and more La Ninas when it's negative. So that just pushed me into realizing we're not being told exactly all the natural causes uh, that are causing the changes we see. And what the journalists do is they blame climate change, and that's very misleading.
Well, more recently, you wrote Ocean Health, Is There an Acidification Problem? For an organization called the CO2 Coalition. Can you tell us about
Yeah.
that? What kinds of people are involved? Why did it get started? What are its aims?
Um, the CO2 Coalition is a group of independent, uh, really high powered scientists who, like myself, do not think that CO2 is the control knob of what's going on. And most of us believe that CO2 is actually a benefit. Uh, Patrick Moore he used to be one of the founders of Greenpeace. And early in my career, I was a big I was very fond of Greenpeace. I pictured myself out in a boat trying to stop a harpoon on a whale, and those are the kind of things Patrick was doing. But we've both come up to the point that Greenpeace has got way too radical, way too political, and it's missing the point of what a good ecologist should talk about. I got invited to it by Will Happer, who read my book. He's a physicist. He designed the sodium guide star, which is used for guiding missiles and astronomical devices with much more accuracy than would have been done otherwise because of the way the atmosphere twinkles. And so he understands a lot about how light and the atmosphere interact. And he asked me, he said, well, I love your book. You look like you understand physics and biology. Would you join the group? And I was totally honored. And there was other people in there like Richard Lindzen, who was MIT's atmospheric scientist, and he's been a long time skeptic. I'm trying to think, is Harrison Schmitt, the last astronaut to walk on the moon, who's a geologist, he's part of that group. So as I looked at Patrick Michaels, who was Virginia's state climatologist, so there's more than I'm leaving out. I can't name everybody right now, but I was just honored to be asked to join this group of people so we could talk about the science of climate change in a much more meaningful way than if you listen to the way the media does it or social media. Usually it's all fear mongering and hype and not really good sound science. And that's what I found the CO2 Coalition to be, is people that's our desire.
Wonderful.
To have good science.
Will Happer, in fact, all of those folks you just mentioned are friends of mine, and I respect them tremendously. I really respect what the CO2 Coalition is doing and explaining to people why more CO2 in the atmosphere is really a good thing, not a bad thing. Now, Jim, in the title of your later monograph, Ocean Health, why is there an acidification problem? There are quotation marks around the word acidification. In the journalistic trade, we call those scare quotes. Why the scare quotes around acidification?
Well, I never thought of them as scare quotes, but be careful about this word, because acidification is often talked about as just a function of atmospheric CO2 that the fossil fuels are adding and then causing the oceans to lose pH, pH to drop. Well, and the oceans are still alkaline. You have to go below pH 7 before you become acidic. So that word is misleading from that point of view. You have the deep ocean has the pH is 7.8, 7.4. As you go down just a few hundred meters, it's much lower than what the surface is. And when that water is brought to the surface, you get a lower pH, and people, oh, well, this is ocean acidification. Well, it's a natural phenomenon, not something caused by fossil fuels pumping CO2 into the surface of the ocean. So the word acidification is just such a loaded term. I decided to put it in quotation marks just to kind of make the readers alert to that.
Okay, great. Now, most of our audience probably doesn't think often in terms of the pH scale. It's just not something that's a common thing for us to talk about. Would you just explain that scale briefly so that people understand why ocean acidification is really a misleading term?
Okay, and I realize when I talk to most people, if you talk about pH as a inverse logarithm, their eyes glaze over. There, you just not going to understand. But really quickly, if I have a pH of 1, that means I have one hydrogen ion for every 10 molecules of water. If I have pH 2, I have one hydrogen ion for every 100 molecules. And so the pH 1 actually refers to the 10 has 1 0, the 100 has 2 zeros. So if I told you there was a pH 7, that would be one molecule of hydrogen ions for every how many molecules of water? It'd be 10 million. 7 zeros.
With 7 zeros.
Now, the pH 7 is considered neutral because if you take distilled water and measure how many hydrogen ions in it, it has one molecule of hydrogen ion for every 10 million molecules of water. When I would do experiments with my students, when you look at how the number of hydrogen ions or the pH affects enzymes, and almost all enzymes have an optimum. So you can have a lower pH be a problem, you can have a higher pH be a problem. But in terms of what's happening in the ocean, if to just call it acidification, it sort of conjures up fears that everything is dissolving. And I've just I write a newspaper article for a local paper here, and they talked about the Dungeness crab is sort of like East Coast lobster. It's the tasty seafood dish out here. But they were talking about the crab were dissolving because of ocean acidification, and it was just totally bogus. And they didn't talk about the way this upwelling brings low pH waters up to the surface, and how when it does that, it brings a whole lot of nutrients in a whole burst of life. So when you think of pH, it could be any different numbers, and you're going to have to look at the local situation to decide if it's a benefit or a problem. But naturally, below the surface, the pH goes down to 7.4, which is still not acidic. So the term acidification is really what the person who coined it was to scare people, and he admits that.
Yeah. You actually mention in your book that Dr. Ken Caldera, who's an atmospheric physicist or scientist at the Carnegie Institution for Sciences Department of Global Ecology, you say that he intentionally promoted the term ocean acidification to generate public fears. And you quoted New Yorker journalist Elizabeth Colbert that Caldera told me that he had chosen the term ocean acidification quite deliberately for its shock value. Now, we're used to scientists talking in terms of objective facts as much as possible. Why would a scientist choose a term for its shock value when doing so actually winds up communicating something that is scientifically misleading at best, outright false at worst?
It's hard to attribute what someone's real motives are without being inside their head. So I can only speculate. But I know in terms of the scientific journals are businesses. And if you can attract a lot of attention, your papers get published more. You get more people that want to keep funding you and doing your research. So if you just say everything is hunky dory and it's the same as it's always been, well, people say, well, big deal. Why do we care about that? But if you say, we're going to climate hell, then people get a little worried. And I know as teaching students, if you say something scary, you have their attention. If you just give something in a sort of a scientifically mechanical way, then a lot of times, they're a little bored, or it doesn't hit their emotional response. So before Caldera sort of coined this phrase, there was hardly anything in the literature using the term ocean acidification. It was a rare term to be used. Once he did that, boom, all these scientists started using that term. And it's sort of, I see it in every paper when they say, oh, there's a problem with these fish or these crabs. They say, well, they suffer from X, Y, and Z, which is well known, but then they say, and probably ocean acidification. And they say that without ever studying whether that ocean acidification has had any effect on them. So it's become just sort of this knee-jerk response that tries to explain stuff without really explaining anything.
That's really interesting. We actually have a video that's supposed to show what ocean acidification is that we can cut to.
This comes from the Smithsonian. Now, this slide showing carbon building up more than ever in Earth's history is pretty misleading.
Absolutely.
We've had much higher CO2 concentration in the atmosphere in the long distant past. And here I had to laugh at this. It's showing a plant wilting apparently because of too much CO2 in the atmosphere. And that's the exact opposite of what happens.
Yes, indeed.
Here was the one about so-called ocean acidification, making the oceans acidic.
And you see from that video, they frame everything as CO2 coming from the atmosphere into the surface of the ocean, where the oceans contain 50 times more CO2 than the atmosphere. And most of the changes in pH, dramatic changes, happen because the CO2 is what we call upwelled, when the waters that are low pH are brought to the surface. So no one talks about it in those terms. If there's an upwelling event that causes low pH, they'll say, well, that water's been more acidic because of what's coming from the atmosphere. But if you look at the biological processes, the way CO2 goes into the ocean, most of that CO2 is turned into organic material due to photosynthesis. And then it quickly, most of it, well, not most of it, but a lot of it quickly sinks to the bottom. And when they talk about it's the most CO2 in the atmosphere ever, if you go back, 200 million years ago, you might have had CO2 up around 6,000 parts per million. In organic life, photosynthesis, as trees covered the contents of it, they took that CO2 right out of the atmosphere. They buried it in the oceans. And so the CO2 by about 250 million years ago was probably about as low as what it is today, if not lower. And it's just this idea that life alters the chemistry, where what a lot of these people are pushing on acidification are saying it's the CO2 that alters life. And it's just the reverse, as you say. And because most plants evolved when there was 6,000 parts per million of carbon dioxide, they thrive on high CO2 levels. And that's why our greenhouses will pump CO2 to make the plants grow better, because that's what they evolved to do.
So is this fear of ocean acidification related to the failure of global average temperature and the frequency and intensity of extreme weather events to rise as much as climate alarmists warned they would?
I would say the school of thought of the alarmist scientists And there's a lot of scientists that stay mum on this. They're not sure which way to go right now. But I think they like to push. If you want to get attention, you want to get published, you want the media to talk about your research, that's a nice thing for someone to feel. So they push all this alarmism. It does say that we're going to have more heat waves. Well, if you look at the EPA heat wave index, right now we've had the 1930s was by far the greatest time of heat waves. Right now it's been no trend if you pull the 1930s out of it, but they push it. And so sometimes I've talked to a few journalists, none of them are scientists. They're journalists. And so they like scary stories because it's clickbait for the internet or for whatever. And so I've had journalists tell me, well, I'm looking for man's comeuppance. So they're not even looking to know the truth. They want to kind of push some kind of fear factor, which I'm more frightened about the way the social media is distorting this than anything that CO2 could do to the environment. Now, it's true CO2 is a greenhouse gas. It's true that it's higher than what it was 150 years ago, but how sensitive our environment is, how insensitive the ocean is to it, is really an open question. And there's a large debate, and people, different scientists will say it's very low sensitivity to very high sensitivity. So that's where we have to discuss things more. And what I come from is, if we want to know how CO2 is affecting things, you sort of need a baseline, or what we'd call the null hypothesis. And so you have to decide what's natural variability. And so if you can say, okay, here's what's naturally happening, then if what happens exceeds that, then maybe we could plausibly say that CO2 has caused that exceedance. But if it doesn't, if it's still within the realm of natural variability, then there's really no effect. Now, CO2 is a greenhouse gas. It probably has some small warming effect, but to turn it into a catastrophe is fear mongering that is something we shouldn't be doing.
Yeah. Yeah, I spent a lot of years as a journalist myself, and in the journalistic profession, there is the saying, bad news is good news is no news, because bad news sells.
If it bleeds, it leads.
And you gotta pay your bills, and that means you gotta sell advertising, and you sell more advertising if you have more viewers, more readers. So obviously you focus on publishing bad news. But Jim, in ocean health, you point out that fears about ocean acidification arise in part from simplistic modeling of how CO2 interacts with the ocean, modeling that focuses pretty exclusively on non-organic chemical reactions, but largely ignores biological reactions related to what the IPCC, the Intergovernmental Panel on Climate Change, terms ocean productivity. Can you explain the difference between the non-organic chemical reactions and the ocean productivity, and why the resulting expectations differ so much?
Well, it depends what you want to emphasize. First I'll just say that there's so many different variables affecting the way the ecology works. You have to have a model, but anybody can make a model, and the important thing is to kind of test that model and see how well it's working. The models that we're talking about, ocean acidification, they are basically, if you put 400 parts per million CO2 in the air above a container of water and let it equilibrate, you will see that the pH will drop to about 8.1. And so that's what the model will say is what's happening now. But they stop there. And what happens is when CO2 goes into the water, it quickly interacts with the water molecules and converts to a bicarbonate ion and a hydrogen ion. And it's those hydrogen ions that lower the pH. But the bicarbonate ions cannot be used directly for photosynthesis. So all the photosynthesizing plankton have developed an enzyme called carbonic anhydrase, which takes those hydrogen ions and the bicarbonate ions and joins them back together to make CO2. So, because CO2 is the only thing they can use to photosynthesize. So there's this natural interaction between organic life and non-organic life that sort of keeps the pH at a certain level. There are other factors, but it the the marine life doesn't allow the pH to just precipitously drop. And even if you look at just the chemical nature without the way life is going to interact with it, as CO2 changes into bicarbonate ions are also a buffering solution. They can eventually, if hydrogen gets too high, it will grab onto the hydrogen. So if you ever had heartburn, you took an Alka-Seltzer, which has bicarbonate ions in it. And that joins the hydrogen ions. It makes CO2. It diffuses into your bloodstream and you breathe it out. And that gets rid of your stomach acid. Well, the same thing will
Never knew
happen
how that
in the
worked.
and the same thing was, so by the time you add enough CO2 by about 7.8, 7.7, it's not going to go much lower than that because it has its own negative feedback to prevent further acidification.
Huh. Well, also in ocean health, you point out that, excuse me just a second, you wrote counterintuitively, and I'm quoting you here, counterintuitively, the total amount of CO2 stored in the ocean not only doesn't correlate with the amount of CO2 in the atmosphere, but also, quoting again here, it does not correlate with the ocean's surface pH. Now that really does seem counterintuitive. Why is it true nonetheless?
Well, I've heard people like Michael Mann say, well, we got to convince the public that we have these problems. We're fighting for the public's mind. And so the simple slogan, or I don't know what simple meme you could call it, is that the more CO2 in the air, the more goes in the ocean, the more acidic. And keep it simple. And because as you said, most people don't think in terms of pH. Most people don't have that understanding, and it usually makes your eyes glaze over if you go into any depth. But if you look at the end of the last ice age, 18, 20,000 years ago, the glacial maximum, the atmospheric CO2 fell to about 190 parts per million. That's lower than what it was in a couple hundred years ago of 280. Now,
That's
the
right
glaciers
close to
covered
where
all the trees.
photosynthesis stops too, isn't it? That's right close to where photosynthesis just stops. And if we had
When
had
it gets,
that, we'd have been in really
I would
big trouble.
imagine it could, but in the ocean, you can still have all these bicarbonate. 90% of the ocean's carbon is stored as bicarbonate ions. So that you have a little more leeway than that. So
Okay.
I wouldn't quite go that far. But you say, well, where did all the CO2 go? Well, you have conservation of mass. It just didn't disappear. The trees are no longer taking it because the glaciers had covered them. So the only place CO2 could go is into the ocean. And what they've calculated recently is during the glacial maximum, there was about 850 billion tons more CO2 in the ocean than there is in the ocean today. And despite that, the surface of the ocean, the proxies they use was only about 8.3 pH, which is a little bit higher than today. So it just because you have more carbon dioxide in the ocean doesn't mean that the surface pH is going to change. And what I try to emphasize is really what controls the surface pH is how much nutrients and CO2 is brought from the ocean's depth up to the surface, and then how quickly the photosynthesizing organisms incorporate that into organic matter and then send it back to the deep.
Huh. Okay. Now, a climate scientist, Dr. Roy Spencer, with whom I'm sure you're familiar, has shown
He's
that
a member of the coalition. I
clouds.
forgot to mention. Sorry, Roy.
Pardon?
I said
Okay.
Roy's part of the coalition.
Yeah, that's right. He
He's
is.
one of the reasons I joined, so I just apologize to him online for not mentioning him.
Yeah, he is a member of the CO2 Coalition as well. He's also on the board of directors and is a senior fellow of the Cornwall Alliance. So we're really delighted to have him. Uh, at any rate, Roy has shown through his work with satellites that that clouds respond to changes in atmospheric temperature in a way that makes them actually function something like a thermostat, limiting both warming and cooling. And some people, myself included, think of that cloud temperature relationship as an example of what could be termed intelligent design of the Earth's climate system. It strikes me that your explanation of how ocean productivity responds to changes in ocean pH is similar, making it a kind of a thermostat for ocean pH. Uh, could that be viewed that way? Is that a reasonable explanation?
I totally agree with Roy's analysis, and I've seen it in a number of papers that you heat up the water, uh, you get more clouds, the clouds block the sun, and then you have a cooling. So there's this back and forth where you kind of maintain a temperature within certain fluctuations. Uh, to uh, make it an equivalent analogy with pH is a little more difficult because there's not that kind of direct relationship. Um, if you have more upwelling, you can bring up more uh, low pH water from the deep up to the surface. Uh, and if there's enough nutrients there, you can have the photosynthesis take everything and bring it back down. So that there's these, I would just call them negative feedbacks. That
Hmm.
there's and as I mentioned a little bit earlier, the more CO2 goes into the water, it makes bicarbonate ions. But as those bicarbonate ions increase in concentration, they start grabbing hydrogen ions and converting them back to CO2. So there's that negative feedback, uh, regardless of how the organic reactions are happening. So it's just a little more complicated than what uh, Roy's thermostat is, but there's definitely feedbacks that keep the pH within a certain realm. But as we've seen over hundreds of million years, eventually the all the ocean life can and all the land life can absorb CO2, store it in dead and living material, and pretty soon the atmosphere has no more. Has very low concentrations of CO2, and it's gonna affect pH, but pH is not gonna sort of if you have a low pH, it's not going to cause the CO2 to go down or go up. It's other things that control pH.
Okay, thank you. That's really good because you've corrected my own misunderstanding there, and I really appreciate that when a scientist does that because I don't have that expertise. Um, but it was comforting, I should say, to hear you talk in terms of negative feedbacks because I guess in a sense that's basically the way a thermostat works. When
Right.
the air in your room gets too warm, the thermostat clicks and the AC comes on. If it gets too cold, the thermostat clicks and the heater comes on. So it's a negative feedback, and I think that's what an awful lot of the climate alarmist movement misses is the fact that nature is far more characterized, I think, by negative feedbacks than by positive feedbacks. And I think the simplest way we know that is just simply that we don't have all of these positive feedback loops running off into just you know catastrophes all over the place. It seems like nature is pretty much robust, resilient, self-correcting. So really appreciate your explaining that. Megan, I think you had another question for Jim at this point, right?
I do, but real fast, I want to say welcome to those of you who just joined us. We're here with Jim Steele, author of Ocean Health, Is There an Acidification Problem? And Landscapes and Cycles, an Environmentalist Journey to Climate Skepticism. And if you have questions, pop them in the comments box and we'll answer them live. Um, so, Jim, one of the biggest fears about so-called ocean acidification is that it's killing coral reefs and depriving lots of fish of that habitat. And our kids are hearing this in school all the time. So, what's the truth about that?
I've written about that for a number of reasons. Um, I even got on Australian radio. They try to trash me as just a ornithologist from California, but coral reefs actually is a very low energy system. There's not a lot of nutrients there, and so corals survive by a symbiotic relationship with these dinoflagellates that do the photosynthesizing. To give for those to photosynthesize, they need CO2. And so what the coral actually do is they pump hydrogen ions into the vesicle where the photosynthesis happens, and they lower pH to about 5.5. And that causes the hydrogen ions and the bicarbonate ions to join together with CO2, and then they can photosynthesize. So it's, to say that more CO2 is killing the reefs from a photosynthesizing perspective is absolutely wrong. They're starving for more CO2, and they go out of their way to make more CO2. The other issue is they say, well, we're having, if you have more acidic waters, if the pH drops, then you're going to dissolve the coral reefs because they're made out of calcium carbonate. And just like if you have a low enough pH, the hydrogen and the bicarbonates join. Well, if it's low enough, the hydrogen and the carbonate ions. Well, none of the coral, and actually none of the shell-forming organisms that make their shells out of calcium carbonate use carbonate ions. So the whole argument, you read all these papers say acidification is going to eliminate these carbonate ions that shell makers need. What all the shell makers use is bicarbonate ions that are plentiful and will always be plentiful. And they absorb that into their body, and they move out some of the hydrogen to convert it to a carbonate ion so they can make their shells. So they do that internally. They're not dependent on what's happening outside of them. Furthermore, if you have dissolution of the shells, it doesn't happen when there's an organic covering. So we have these coral polyps covering their skeleton. The external environment is not affecting them. The ions can't get through all those membranes. The same thing is for you have clam shells or snail shells. They have an organic covering that prevents ions from penetrating to the shell. So it doesn't affect them until they die and they shed that. So you can have these clams and mussels outside very low pH vents of volcanoes, and they survive because of that kind of protection. And as we talked about feedbacks, when a shell dissolves, the calcium and the carbon ions will separate. And now you're adding carbonate ions, which are buffers, just like the bicarbonate. The carbonate ions will now grab onto the hydrogen ions and raise the pH back up. So that's a negative feedback that happens that prevents further dissolution and further drop in pH. So it's from every different angle I look at this, it's just absurd the way this gets pushed in the media.
So if we turn to fossil fuels here for a minute, which also gets pushed in the media, people think burning fossil fuels and emitting CO2 into the atmosphere, they claim that the result is that we're adding 2.3 billion tons of CO2 to the oceans every year. You argue that that's not something to worry about. Is this why? How long at that rate would it take to put enough CO2 into the oceans to match its level at the end of the last ice age? And why would that be important?
Well, what they've calculated, and because of upwelling, there's like 60 billion tons of CO2 leave the ocean every year. And 60 billion tons go into it, or roughly, and there's a little left over. So what they argue is that this 2.7 is the residual that's going into the ocean. Well, if you compare that to the 850 billion billion tons of CO2 at the end of the ice age, for the oceans to absorb the same amount of CO2 from fossil fuels, it would take roughly 350 years. And it's sort of by simple math of dividing 2.5 into 850 billion. But again, because of the way the trees might absorb it or other kinds of processes, I can't give you the exact number, but but say it would take 300 years at least for the oceans to have as much CO2 as they did at the end of the Ice Age.
Yeah. Okay. You know, I find an awful lot of the time that the people who really are, you know, I hate to just keep using the word alarmist over and over again, but that really does seem to fit, that they have a tendency to take big numbers like this, you know, 2.5 or 2.3 billion tons of CO2. And everybody hears that and they think that's huge. And they don't put it in context with compared with what? And it turns out that it's a tiny, tiny fraction of a percent of all the CO2 that's in the oceans. And it's just, you know, we need journalists who are willing to do the extra work to put things into perspective, to get some proportion. But we also, frankly, need scientists who are willing to do that work for the journalists so that the public really can see things with a bit of good perspective. Now, Jim, what similarities are there between how and why climate models lead to unwarranted conclusions about anthropogenic global warming on the one hand, and how and why ocean carbon cycle models lead to unwarranted conclusions about ocean acidification? Are both of these examples of an over-reliance on models by a lot of scientists at the expense of real-world empirical observation? Or what other explanation is there?
Well, my explanation would be that you need these models. They get half of it right, but they don't have a good model of natural variability, of the way organisms interact with the environment, partly because it's so complicated. And to give you, the Pacific Decadal Oscillation is now considered one of the four biggest cycles, like El Nino and La Nina, affecting temperature, climate, the circulation of ocean currents, and how much upwelling happens and how much marine productivity happens. Well, it wasn't until like 1997 that the Pacific Decadal Oscillation was identified. And the author who helped work out the details of that, they wrote a paper. He was a co-author of a paper that said the Pacific Decadal Oscillation could explain the last 100 years of climate change along the northwestern coast of North America. And it's so a lot of this fear happened because they made their models based on insufficient evidence. And once they had that, they just kind of extrapolated out into the future these fearful things, not realizing there was much more to it. There were much more negative feedbacks. There are other things that could explain what they're seeing. So if you see a natural ocean cycle causes warming for a while and then causes cooling, you're not afraid. You just say, okay, we got to adapt and live with this. But if you just see half of that cycle and you think it's caused by CO2 and you think more CO2 is going to keep that trend going up and up and up, then you get afraid. And so I think it's just, part of it is just they haven't understood enough of everything that's going on. And hopefully we're developing much more information and a better understanding of cycles. I looked at all the way the fishing data in the Atlantic worked, and we can see these cycles of warm water going into the Arctic, melting the ice. And at the same time, you'll see temperatures in Greenland go high in the 1930s. Then that ocean water goes back. And so now it cools and temperatures cool. And then right now, we see the fish in the ocean water have moved into the Arctic from the Atlantic, causing the same kind of warming. But it's something called the Atlantic multi-decadal oscillation, which is also relatively new to our understanding, is now reversing. So what I think you'll expect to see within the next 20 years is as that warm water retreats out of the Arctic, sea ice is going to come back, temperatures in the Arctic are going to start to decline. So again, I think it's just ignorance. And it's because of all this stuff is really in its infancy.
Huh.
Did I stump you?
Sorry.
Well, I've got a question from Facebook for you, actually, that I'm pulling up.
All right.
Joe wants to know, where does the observed bleaching of coral reefs come from, if not acidification?
It will come from a number of different things. A lot of it can be a rise in temperature. Sometimes can be cooling in temperature. Probably one of the biggest bleachings off of Florida happened because of cold temperatures. I don't know if you remember, it got cold enough, iguanas were getting stunned and falling from the trees. So you can have temperature changes. You can have a high windstorm, a high rainstorm that brings a lot of fresh water, and that throws the balance off of the way the corals absorb nutrients and whatever, and that can cause bleaching. What is really interesting is, these coral have been around for 200 million years. They've adapted to all sorts of changes, and what they're now knowing, because we're so advanced in understanding genetics, that the symbionts that live within the coral, they have a very narrow temperatures or freshwater conditions that they can live in. If those change, they have to get rid of the symbionts have to leave. And sometimes what they see in the corals, and these symbionts are what give them color. In the winter, the coral will keep a lot of symbionts and it'll be very colorful. As the temperatures warm, the way of regulating how much photosynthesis can happen, because photosynthesis also produces these oxygen radicals. The coral expel some of their symbionts. So, and if it gets too hot, they'll expel them all, but they can take them back in. And what they're finding from the genetics is there are hundreds of different species, if you will, that have different temperature ranges, different pH ranges, or whatever. And a coral will get rid of one symbiont and then bring in another, and they can watch this change happen in just one season. So these coral have been able to survive hundreds of million years of tremendous climate change by altering which symbionts they're using, which gives them tremendous versatility. They don't have to evolve over hundreds of years of having some lucky mutation happen. They just pick and choose the different symbiotic algae that best fits the conditions. Hope that gives you a little idea.
Yeah,
That's fascinating. Yeah.
It is fascinating.
That answers your question. Well, you actually argue in your book, Ocean Health, that our CO2 emissions, far from causing collapse of marine life, are instead actually enhancing it. So can you tell us what's really happening there and how it's happening?
Well, basically, the whole marine food web starts with the plankton that photosynthesize, that they make organic carbon, that then zooplankton, copepods or krill or whatever, feed on, which then are fed on by the bait fish like sardines or anchovies, which then get fed on by the bigger fish and the whales. I live here in Pacific, and the humpback whales have been coming back about 12% a year. And I used to lead some whale watching trips. We'd have to go 20 miles offshore to find a humpback. Well, now I can find 5 or 6 offshore, and as they lunge out of the water, you can see the anchovies jumping out of their mouths. So there's this abundance that's going on. It's pretty spectacular. But anyways, once you have this upwelling, that you have enough nutrients and enough CO2, the algae can start that whole food chain. And every year they can start a whole new food chain. So it's that a lot of these marine organisms, if we don't overfish them, they're going to respond very quickly. I know they just reopened some fisheries up by Oregon because within 5 years, all of a sudden it came back. The key to that is photosynthesis. And the key to photosynthesis is upwelling. If you don't have this upwelling, you don't bring nutrients to the sunlight, and you bring also CO2 with it. So they do studies now looking at how much CO2 could affect photosynthesis, and different organisms respond differently. So some bacteria flourish with more CO2, some they don't see any change. And part of that reason is because these photosynthesizing organisms are starving for CO2. A number of them have developed the ability through this enzyme carbonic anhydrase to convert bicarbonate ions into CO2 so they can then use it for photosynthesis. So if you did an experiment, you added CO2 to the water, you'd just be actually creating a lot more bicarbonate ions, and you wouldn't see uh, a, a tremendous change. But so you say, oh, well, there's really no effect to CO2. Well, you could argue that because of the way they use this bicarbonate ions, but no studies show more CO2 causes less photosynthesis. And you also say, well, if to photosynthesize you need other nutrients, and maybe you're not going to get enough nitrogen. Well, we know there's some bacteria that fix nitrogen, just like beans have a bacteria that fixes nitrogen, and we plant those to make the crops more productive. There are trichodesmian, it's called the ocean sawdust. It responds to CO2. The more CO2, the more nitrogen it makes. So there's a number of things that kind of coalesce here where that more CO2 is just beneficial.
Yeah, that's a
interesting.
message that the Cornwall Alliance has been pushing for a long time, and it was wonderful to see the CO2 Coalition get started up, because really more CO2 in the atmosphere means plants grow better. They grow better in warmer and cooler temperatures and wetter and drier soil, and they make better use of soil nutrients and all sorts of neat things. And the result is more food for everything that eats plants or eats things that do eat plants. So that's just seems to
Absolutely.
be a win-win situation. And you're explaining how the same thing goes on in the oceans that's going on land and in the atmosphere. Now, one of the things that I found really interesting in ocean health was when you discussed why it is not ocean acidification, so called, that led to the temporary collapse of Oregon's oyster farming industry a little over a decade ago. I found that really fascinating. A lot of people have used that collapse as evidence that ocean acidification is real and it can have devastating consequences. Would you just explain that briefly for our viewers? It's something that has come up in the news over and over and over again over the last about 13, 14 years.
And I just published something in our local newspaper going at this again. The To start off with, different oysters respond differently. And the native oyster that was called the Olympia oyster, it broods its larvae inside its shell. And the reason they do that, or the reason that brooding makes them successful, is now they've insulated them from any changes in pH. And along the west coast of North America is where some of the most intense upwelling in the world happens. And so those oysters were adapted to that, but they got over harvested and almost extinct. So the oyster fisheries brought in the Japanese oyster that didn't evolve in a highly uh, upwelling environment and low pH. And so the hatchery people didn't realize that those larvae, they have about a 6 hour window when they first form their shell before they can have the shell with the protective coating. It has about 6 hours. It's very sensitive to pH. Well, what the fisheries were doing is they would pump water out of the estuary where all the oysters normally grow, pump them into tanks, and they do it early in the morning. Well, early in the morning is the lowest pH in an estuary's water because photosynthesis hasn't happened all night, and just the respiring of the metabolism of all the sea creatures lowers the pH. At the same time, you had an upwelling event, and that upwelling event brought this deep water into the estuary that was low pH, and they coincidentally pumped that into their tanks. So they brought the pH in their tanks to such a low level that the larvae, their 6 hour window was compromised, and they didn't form the shells well, and there was a lot of deaths of their larvae. Since then, they have realized pump later in the day when photosynthesis can naturally raise the pH. a couple of scientists developed meters that can warn them when there's an upwelling event, and so they don't pump the water then. And those two fixes have totally averted the crisis, and you don't hear about this kind of damage anymore. It's not that the world's changed. CO2 in the atmosphere has got greater, but the oysters are surviving as well as ever. And that upwelling brings nutrients into the estuary that allows the oysters to grow well once they pass that little 6-hour window. So it's just, again, it's misinformation of understanding how all that works. And the way that word, and the reason I say ocean acidification is in quotes, is because people misunderstand this natural effect of upwelling that lowers pH. So, I'm blown away of how people got all, the whole governor of Washington, they started like an ocean acidification school at Washington University. They got a lot of grant money pushing ocean acidification. Dr. Cliff Mass is an atmospheric scientist there, and who used to write for the Seattle Times. He was well respected on what he does. He said this was a natural event. The people at the university got mad at him. The governor got mad at him because he didn't make it a human-caused catastrophe. So there's money to be made if you're the guy that's saving the world from the catastrophe. What I hope folks like ourselves can do is save the world from the people that are trying to save the world.
Right. Right.
Well, you taught ecology at San Francisco State University for many years, and I suspect you observed how prone much of academia is to the one-sided alarmist view of many ecological subjects. Obviously, in Washington as well, they are that way. What can our listeners do to counter that influence among college students?
Well, what I'd encourage them is, Einstein said, never stop questioning. And I'll give you, I have one of my colleagues teaches policy to deal with climate change. And he came on I do local bird walks at my park, and he came on one of the walks, and he mentioned climate change. And I said, well, you're talking to the wrong person. I don't think it's a problem. And I said, well, let's not talk about it on this talk. Let's sit down and discuss it. So when we did, the first question I asked him was, what makes you believe that CO2 is causing all these problems? And he got real sheepish. He said, I was afraid you're going to ask me that, because I'm just trusting what these other people say. And almost everyone I argue, as soon as we try to discuss details, will back off. And it's this myth of this 97% consensus. He would be one of those people that would say, oh yeah, it's CO2, without ever looking at it. And so they've done the alarmists, and I think we just have to use that term sometimes, the alarmists have done a good job of saying everybody believes this is what's going on, and if you don't believe it, you're a fool. And people have to stand up to that. If you look at a number of real sensitive, most scientists don't respond to the polls that ask them, or the surveys that ask them what they think CO2 is doing to the atmosphere. They'll all agree that it's a greenhouse effect and it's increased, but they'll stop there. And that 97%, what I was told as a scientist, as soon as you become
Looks like Jim is frozen up there somehow.
Yeah, I'm going to log in real quickly if you can hear me.
Got you back, Jim. Thank you. Jim?
Okay, we lost him there for a second.
Yeah, he should be able to log back in pretty quickly.
There you are.
Megan,
there's Megan.
There he is. Got you back. Thank you.
What is this 97% consensus is a myth. Think for yourself a little. And a story that my father always told me was the Chicken Little story. And I think that came out of Scandinavia hundreds of years ago. it, but the thing to remember in that Chicken Little story is they're all running around. Oh God, it's, the sky is falling. He gets everybody in the barnyard to run around screaming with him. And they meet Foxy Loxy, who says, well, if you're afraid of this stuff, I have a burrow. Why don't all you chickens and ducks come into my burrow? And then you never hear of the chickens and ducks again. Well, I think partly what we have to be very much aware of is that a lot of Foxy Loxies around. And if you start running around like Chicken Little, it's going to be the end of you. For your own survival, do what Einstein said, never stop questioning. And one of my favorite scientists from the 1800s, he just said, the improver of natural knowledge, it takes skepticism as his highest duty, and takes blind belief as the greatest sin. And if people just check themselves, as soon as you blindly believe something, you don't investigate it a little more, you're going to be led astray in so many different ways.
It's amazing how much wisdom we can get from children's stories through
Yeah,
the years.
absolutely. Yeah.
Jim, it has been wonderful to have you on the program with us. I hope that you will come back with us sometime and discuss more of your work, more of the work of the CO2 Coalition.
Well, I am honored to be here, and anytime you think I can be useful, I'd be glad to come on. I could talk another couple of hours if you want to keep going.
Oh yeah. No doubt. To me, it's
awesome.
a great opportunity for education for me, for Megan, for all the people who see the program live and the people who see it later on as well. So thanks very, very much. Appreciate having you on, and take care. Have a great week.
Thank you.
Don't
You
let
too.
COVID bite you.
Paper ocean health. Is there an acidification problem? It's our special gift this month to donors who request it as our thanks for a 100% tax deductible gift of any size. We'll send it to you. To make your donation, click the link in the comments box of this live stream and get to mention promo code 20-07. You can link.
Okay, thank you. Megan, you broke up there a lot of times, so I'm just going to repeat a little bit of that. Ocean Health, Is There an Acidification Problem? By Jim Steele, whom you all just heard, is our special gift this month to donors who request it. As our thanks for a 100% tax deductible gift of any size, we'll send this to you. All you need to do is make your donation and ask for it. You can make that donation by clicking on the link in the comments box of this live stream. And don't forget to mention promo code 2007. Well, this offer expires at the end of this month, and our supply is limited, so don't delay. Your gifts are essential to our efforts to promote biblical earth stewardship and economic development for the poor, tied together with the good news of salvation by grace through faith in Jesus Christ, who, by his death on the cross, paid the penalty for sin, and by his resurrection assured salvation for all who trust in him and repent of their sins. Thank you very much for joining us.
Yes, until next time, thanks for joining us. God bless, and we'll be back here next Tuesday at 7 p.m.